Good morning, everybody. Can I have some indication that somebody hears me? You're more than welcome to just put in chat if you don't want to say anything.
Good morning, Professor.
Thank you. I know it's difficult. Whoever chooses to say good morning ends up being sent a screen, so I understand the reluctance. All right, let's see what we're doing. Okay, so what I was going to do today was continue on with the sample test or the practice test here. And just a reminder, I'd like people to have their video on, please. All right. Yeah, because I actually didn't go over, well, I did the other day, but does anybody have any other questions about questions 1 and 2 on the test? Does anybody have any questions about questions 1 and 2 on the test? That's the enthalpy question and the bond energy question. All right. Everybody okay with those? I mean, I did go over them at the end of the last Zoom session. So if you weren't here on Monday, that's when I went over them. So, and nobody has any other questions about those, right? The other one I went over on Monday was the Hess's Law one. So I won't do that again today, but I will do the Bohr transitions question, and we'll go with that. Okay, so you'll notice with the Bohr transitions question, and we went over this, I think, a couple of days ago. I think it was last Wednesday, actually. I went over this. You get these equations which allow you to determine each of these. So you've got 3 questions. You'll have wavelength, you'll have energy, and you'll have frequency. They may not be in that order, but they may be. I don't know. I think I've randomized them actually, but you can, you'll get one of each of them. But well, I'll do them in order first. I'll do the wavelength one first. And what it's asking for is the wavelength in nanometers of a photon that results from the electronic transition from n equals 8 to n equals 2. So what we're going to do first is find the energy, because that's what involves these n values here. So when I went over these, so to get the energy, we got the n1, the n2 values. Now, if you choose, it depends on which ones you choose for n1 and n2. You're going to get the same numerical result regardless of what you choose for n1 or n2, whether it's 8 or 2 or 2 and 8. It's not really going to matter numerically. However, if you put the 1 over 2 squared first, put the smaller one first, and the larger one second, you'll end up getting a positive value for energy, which is going to be more palatable to you in the long run. And the energy then would likely be a positive value, and then your wavelength will be a positive value as well after that. So what I would do is do 1 over 2 squared minus 1 over 8 squared and come up with the energy. And the energy is going to come out to be joules. So let me show you. I'll get the calculator here. So it's effectively 1 quarter minus 1/64 is how I would do it. And on this calculator, I'll do 1 over x minus 64 and then 1 over x there. And that gives me whatever the result is for this. Is everybody okay so far? Does anybody have any questions? All right. So then we multiply that by 2.179 EE negative 18, and I'll do 8. There we go. Does the plus minus and the negative 18 and hit equals. And now that gives me my energy, which is 5.107 times 10 to the negative 19 joules. Any questions so far? The next thing we need to do is, you see what we're looking for is lambda, which is the wavelength. That's that symbol down there. To get to lambda, we need the nu, which is the frequency, and we can get the frequency from this equation, which involves the energy. Now, down here in the question 4, I've got another set of things here that allow me to determine what values these things actually have. So the speed of light, 2.998 times 10 to the 8th meters per second, and Planck's constant, 6.626 times 10 to the negative 34 joule seconds. You'll notice that when I do this, I do put in the units as well. So the next step is to, remember we're after wavelength, so we have to get frequency first. So that would be nu equals E divided by H. E is what we just calculated. And H is Planck's constant, which is there 6.626 times 10 to the negative 34. And the unit there is joule seconds. So you'll notice the joules cancel. And when I do that, I stick that in my calculator. And this is where it's really important to make sure you are using your EE or exponent button. So I'm just going to use this entire thing here, 6.626, and then EE, and then negative 34. And it comes out to be that value, which is going to be, well, on a regular calculator, it's actually going to present it to you in scientific notation. And I'm not sure on this one how to convert it to scientific notation. I wonder if I just hit EE here, if it'll do anything. No, it won't. Okay. Anyways, so in this case, I'm going to have to count backwards to get to the decimal here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So it looks like it's 7.7 times 10 to the 15th. Can somebody please confirm that I'm right on this? That it's 10 to the 15th and not 10 to the 14th, that I didn't miscount? Because on a regular calculator, it wouldn't be a big deal. Hello? Can somebody do that, please, for me? Just in the calculator.
I think it is 14.
I got
14. 14. Thank you.
Sorry, I was working the problem.
All right. No
yeah,
worries.
It took me a minute. I was like, wait, is he wrong?
Well, I had to do it. I had to count manually, which was not desirable, but you wouldn't have to do that in your calculator. It's kind of annoying that this one does that. I wonder if I shrunk it, if it would do anything. No. Okay, so that's going to be the frequency. Now I need the wavelength though, and C equals nu lambda. That's the formula we're given. So lambda equals C over nu. C is 2.998 times 10 to the 8th meters per second over 7.708 times 10 to the 14th. And that's seconds to the -1 or hertz. They're really the same thing. That gives meters, but we're looking for, if you look at the question, it's looking for the wavelength in nanometers. And you are given a conversion here to go from meters to nanometers. So we'll go ahead and use that. So it'll be times 1 nanometer over 10 to the negative 1 times 10 to the negative 9 meters. And I'm going to go ahead and put the answer up here. So when you're doing that, you've got to be a little bit careful. And where is it? Here. And you could divide it by, if you want to put 1e negative 9, make sure you do that. 1e negative 9, not 10e negative 9. That's what I sometimes see people do. And there it is there. Whoops. No, I didn't do the other part. Hang on. I didn't do the division by the other thing here. All right. That doesn't seem right. I'm going to do this again. That seems better. All right. And then divide that by 1e negative 9. There we go. 388.9 nanometers. And that's what you'd put as your answer down here. Does anybody have any questions? Now remember on the test, well actually you can't see it on the practice test, but there's a box down the bottom that allows you to show your work. So I'd recommend putting all your work, including units, down into that bottom box. This generally annoys students, that they don't feel like they should have to do this, that they feel like they should be able to just maybe email me their work or something like that, or upload their work to a Dropbox. The problem is though that you get the answers to the test as soon as you submit it. So it'd be easy enough to go back and readjust your work to make it look like you had actually done the work, even if you've gotten the wrong answer. And I don't want people to be able to do that. So the only way that I can really police that is to have people actually put their work in during the test. So I have given you some extra time on the test to do that. So I don't want to hear complaints about people having to put their work in. I mean, on a regular pen and paper test, you have to show your work. So, you know, don't think you get out of it just by being on the computer here. All right, the next one, we're looking for the energy. It's in Zeta joules. Now I do have a Zeta joule conversion here, so we'll make sure we make use of that. And we're going from n equals 8 to n equals 5. Does anybody have any other questions about question 4? Okay. So we're looking for energy. So we're just going to use this one equation here. And again, you know, the equation, oops, there was a chat here. Okay, no worries. Okay, 2.179 times 10 to the negative 18. And the Rydberg constant's there, so you can, it's the same thing. And it'll be 1 over, and I do 1 over 5 squared. Well, I was going to put it over minus 1 over 8 squared. Okay. That'll give me the energy. You notice it'll come out to be joules here. and this is another way of doing it. I can just do times and put that in parentheses. 25 1 over x minus 64 1 over x, close parentheses. Here we go. So same result, 5.311 times 10 to the negative 20. Joules. But we need the answer in zeta joules, and I do have a conversion there. So it'll be 1 zj is 1 times 10 to the negative 21 joules. So divide that by 1e negative 21. There we go. So 53.11 zeta joules. So the reason I do that is so we end up with a number that you don't have to put in as a scientific notation. Okay. Any questions about number 5? Any questions? All right. I'm going to do a poll here. How do you feel so far about number 4 and 5? Okay, I'll give you another 5 seconds. 4, 3, 2, 1, 0. So there you go. All right, so does anybody have any questions? Okay. All right, the next one, we got frequency. And frequency is going to be, again, we need to get the energy, same deal. Actually, let me get rid of all this here. I'll start with a clean slate. So the energy is going to be 2.179 times 10 to the negative 18 joules. And this will be 1 over 2 squared minus 1 over 14 squared. Again, trying to get that positive value there. Okay. Clear. 4 minus 14. Okay, so that's the part in the parentheses. Oops, clear that. I think I hit it twice. Okay. So that's the, it's part in parentheses. Multiply that by 2.179 times 10 to the negative 18. And there you go. So 3.891 times 10 to the negative 19 joules. And then you've got E equals H nu. We're looking for nu, which is the frequency. E over H, and the frequency is going to have to be in terahertz, and we'll get that sorted in a second. 3.891 times 10 to the negative 19 joules times over 6.626 times 10 to the negative 34 joules seconds. That's Planck's constant. Times, now we need 1 terahertz is 1 times 10 to the 12th hertz. So 1 THz on top, 1 times 10 to the 12, whoops, positive 12 hertz. So you'll notice that the joules will cancel and the per seconds will cancel with the, oh, I think I made a mistake there, didn't I? We need the hertz on top here. Or do I? Hang on. For some reason, the so see that's seconds to the -1, and what did I do wrong here? That's hertz. Seconds to the -1. E equals h nu. I've made some kind of error here. It's 1 terahertz. That's the seconds -1. That'd be 14. Did I make a mistake with the question? I don't think so. Let's see, 1 terahertz. 12 hertz. Yeah, some reason that doesn't look like the units are cancelling properly here. Seconds to the -1. Oh, okay, no, it's all right. Okay, no, it works. Okay, it does work. Now the hertz here, this is the reason it's confusing. The second to -1 is equal to hertz. So you'll notice that the seconds and the seconds to the -1 here cancel. That's how that works. So I was no, I was right. I just couldn't see how those were canceling out, but now that's how they cancel. Had to be that way. All right, so 3.891 times 10 to the negative, whoops. Let me clear that out. Times 10 to the negative 19 divided by 6.626 is 10 to the negative 34. Okay, that gives us that, but we want it in terahertz, so divide by 1e12. And that would be 587 terahertz. 587.2 terahertz. Okay. All right, so does anybody have any questions, especially about the way that the seconds and the hertz cancel there? That confused me for a second, but it might confuse you too. So I just want to see if you understand now how those cancel. We end up with terahertz at the end.
Yeah, it confused me for a second, but then I realized it now.
Yeah. Well, confused me too, Michael. Clearly, you know, I go, hang on, why is this canceling? But that was the reason. Because hertz is per seconds or seconds to the -1s, and the Planck's constant is joules seconds, not joules per second.
Yeah. It's interesting.
Yeah. Does anybody have any questions? Any other questions about number 6? Okay. Now number 7, this is the one where we go through and, oops, didn't want to do that. Sorry. I don't know if the set's valid or not yet. Sorry about that. I didn't mean to choose an answer for that. So hang on. Before we choose any answers, let's go back and review here. Let's look at allowed values. And allowed values are for n. It can be 1, 2, blah, 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 blah. L can be 0, 1, up to n minus 1. So it depends on whatever n value you have here. The m sub L is negative L through to plus L. And the m sub S is going to be plus a half or minus a half. If you weren't here when I went through this, this is going to look like nothing you've ever seen before in your life. It's going to look like Chinese. So just be aware of that. I'd recommend you go back and watch the Zoom session where I went through this, because I'm not going to give a full lesson about it now. There's just too much to talk about to get you to a full understanding of why these are the way they are. Anyway, those are the allowed values for each of these, and we're going to go through and see if these are valid or not. N equals -4. Well, clearly that's not valid because N can only be 1 and 2. So it looks like N is out of range, so the set's invalid for that one. Anybody have any questions about number 7? Okay. Number 8, N equals 5. Yeah, that's allowed because 1, 2, up to anything. L equals 2. Yeah, that's possible because L can be anything up to 4, which is N minus 1, because N5 minus 1 is 4. So 0, 1, 2, and 3, and 4 are all legal values, so the L value is okay. M sub L is -1. So the M sub L value can go from -2 up to 2. So -2, -1, 0, 1, or 2. So that's okay. So -1 is an allowed value. And M sub S -1/2, that's allowed. So the set is valid. Does anybody have any questions about number 8?
I'm sorry, why was number 7 invalid?
Because the N value was -4.
It's -4.
Yeah, see that?
I didn't see the minus, thank you.
Yeah, okay. No worries. Okay. Number 9, N equals 3. That's an allowed value. L equals 5. That's not an allowed value because L can only be 0, 1, or 2 because it can only go up to N minus 1. So that's invalid because L is out of range. Any questions about number 9? Okay. Number 10, well, N is -2. That immediately means it's out of range. You just need just the first one. Once the first one's out of range, then it's all invalid. All right, does anybody have any questions about 7 through 10? All right, so regardless of whether you were here or not, tell me how you feel about 7 through 10. So I think I'm going to get some I don't understand it alls here, I'm sure. Okay. All right, so out of the understand halfways here, any questions that I can answer here? Any questions? Well, you know, it's your party, not my party, so. All right. Our electron configurations. So for this one is looking for the electron configuration of Mg. So what I would do is I would find Mg here and I would write out the written one just for kicks. Be 1s2, 2s2, 2p6, 3s2, and that would be it. That's as far as it would go. 2 plus 2 plus 6 plus 2 is 12. So we know that that's correct. So now I have to find the one that matches that. It ain't that one. 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 That one looks pretty good. So that would be the answer. So whatever matches that. Does anybody have any questions?
So how would that be the answer?
How would it be the answer? So you got 1s2, 2s2, 2p6, 3s2. See, it matches the number of electrons in each of the shells.
Okay, thank you.
Yeah, no worries. Any other questions? All right, well, how do you all feel about that one? Five, 4, 3, 2, 1. You all feel pretty good about it. All right, good. I like that. All right, heat capacities. Now, I went through these. I did go through these, well, it was a couple of weeks ago now. I think it's a day after, well, a day after that week I was after spring break. So the first day I came back to teach. So I went through these, but I'm going to go through them now as well. So we'll do 13 first. I'll do both of these here. Now remember also that I do have videos for each and every one of these problems or problem types down below. Okay. So what are we looking for? We're looking for the what was the initial temperature of water. Okay, so a sample of metal is dropped into 168. I like to draw a picture here just to kind of make it a bit bigger here. There we go. So we've got a metal. This will give us our information a little bit, and it's going to go into the water. The metal has a certain temperature. It's 74.75 grams. And it's 294.3 degrees Celsius. And it's being dropped into the water, which is 168.05 grams. And what we're looking for is the initial temperature of the water. What we are also told, though, is that the final temperature is 29.3 degrees Celsius. Now, the catch here is that the 29.3 degrees Celsius is for both the metal and the water because it's at equilibrium. So even though it does say the temperature of the metal, that's also the temperature of the water as well. Does anybody have any questions so far? What we're looking for has to do with the water. So what we should do first is deal with the metal. We did this in lab, by the way, as well. So Qm is equal to mass of the metal, C of the metal, delta T of the metal. And that means that what we're looking for here is the Q value, how much heat was released by the metal into the water. So we've got 74.75 grams times the heat capacity of the metal, which was 2898 joules per gram per degree Celsius. And then that's times the delta T value, which is the change in temperature, which is 294.3 minus the final temperature, which was 29.3. So when we do all that, we come up with a value for the heat released by the metal into the water.
Wait, wouldn't it be final temp minus the original temp?
It really doesn't matter because what we're trying to figure out is just I'm not really that worried about the signs here. You could do it that way. And then it would be a negative QM and positive QW. You could do it that way. That's fine. I'm not stopping you from doing it that way. What I'm saying is it doesn't really matter that much. Two 2898 times, and then it'll be 294.3 minus 29.3. Okay, so it'd be 57. We'll go 5740. I don't. Yeah, 5741 joules. And that's also going to be equal to QW, Now QW is equal to mass of water times C of water times delta T of water. And what we're looking for there is the delta T of the water, because that's what we're interested in. And it's going to be Q of water over M of water times C of water. Now the Q is 5741 joules. The mass is 168.05 grams. And the heat capacity, I think it's 4.18 here. I just want to make sure. 4.184. Z. Okay. And that comes out to be, this gives the change in temperature for the water. I'll divide that by 168.05 and divide that by 4.184. Okay, so it comes out to be 8.164 degrees C. So the question was asking, though, what the initial temperature of the water is. Now, looking at what happened here, the temperature of the metal went down. It went down from 294.3 to 29.3. So the supposition is that the water must have gone up in temperature to get to that point. So it must have been lower than that. How much lower? Well, it's going to be 164 degrees lower than that. So the initial temperature of the water is going to be 29.3, and this is important, minus 8.164 degrees Celsius. And that's going to give us our final answer, which is going to have one decimal place, by the way. So 29.3 minus 8.164, I'll probably do that in my head. That'd be 21.1 degrees Celsius. All right, does anybody have any questions? Okay, how do you all feel about that one? Okay, 5 more seconds. 4, 3, 2, 1. All right, everybody feels good about it. That's good. I like people feeling good about it. This is the other one, which is the temperature of the metal. It's a little bit different to this problem here. I'm going to go through it. Even though I know people felt pretty good about the last one, I'm still going to go through this. It's a little bit different to the previous one. So same kind of story, but we've got 58.40 grams. And we've got 22, let's see, what is that? We don't know the temperature. We don't know the temperature. And it's dropped into water, which is at 27.0 degrees. And we have a mass, 125.90 grams. And I think that's all the information we have. All right. So it gets dropped in there. And then it says the temperature. Oh, sorry. The initial temperature of the water is 22.3. I'm sorry about that. Looking at the wrong thing. The final temperature of the water is 27.0 degrees. And that means that's also the final temperature of the metal as well. right, so that's what we've got so far. Anybody get any questions? We have all the information about the water here. We're looking for the initial temperature of the metal. So we'll go ahead and let me clear that out, and I'll draw up a little bit higher. Make sure I have enough room here. See, so the mass here is, we're looking for the mass of the water. So we're looking for times the heat capacity. And the change in temperature, which is going to be 27.0 minus 22.3. $125.9 times 4.184 times 27.0 minus 22.3. Okay, so 247, let's say go for 2476, but we'll go for 2480 in this case, joules. And then that would also be that's the Q of the water. This will be the, Q of the water. And that also will equal the Q of the metal, so the heat released by the metal. So we do the same thing here. QM equals mass of metal, C of metal, delta T of metal. We're looking for delta T of the metal, which is going to be the Q of the metal over the mass of the metal over the C of the metal. Q248 joules divided by the mass of the metal, which is 58.40 grams. And the C of the metal, which is given in the problem, 0.2435. Joules per gram per degree Celsius. Divide that by 58.4 divided by 0.2435. Okay, so it's 174.1. We'll go with 174 degrees. So that's the change in temperature of the metal. Now the initial temperature of the metal, T initial for the metal, is going to be 27.0 degrees plus 174 degrees, which is going to be 301 degrees Celsius. So this is different from the previous one where we subtracted. Here we added. The reason is because we recognized that the temperature of the water went up. It went up from 22.3 to 27, which means that the temperature of the metal must have gone down. How much did it go down by? Well, the delta T. And that's how we know we have to add for 174 to that to get the initial temperature. It started at 301 and went down to 27. All right. Any questions about this one?
So for the initial temperature, we're basically adding.
Yes. But did you see, Michael, on the previous one, we subtracted?
Oh, yeah. Okay.
So it's not it's not a constant thing. It depends on what's happening to the material we're actually asking about. Here we're looking at the metal, which went down in temperature. In the previous one, we were looking at the water, which went up in temperature.
Thank you.
Okay. Any other questions? Okay, so question 15, what energy is released when 9.1 grams of A is reacted? And we're given a reaction here along with the delta H value. All right, so we do this by doing 1059.1 grams of A, and we're going to do, we'll do times 1 mole of A over the molecular weight, which is 188.8 grams of A. So that gives us moles of A. Now the key part here is the relationship between A and delta H. So 2 moles of A, which goes on the bottom here to cancel the moles of A on top, produces 1840 kilojoules. And there's no negative here because I know it says minus, but we don't put a negative here because we're looking for the energy released, and it's not a negative energy that gets released. So it's kind of a semantic thing. So that's why I don't put the negative in front. Now that gives us kilojoules, but what we're looking for is megajoules. And I've got a conversion here where 1 megajoule is equal to 10 to the 6 joules. But we also know that 1,000 kilojoules is equal to 1 megajoule based on that. So 1 mj is 1,000 kilojoules. Remember that that would be 1,000 joules. So I'm just doing a little shortcut here to get to that point. Does anybody have any questions about that conversion there? How I'm getting that? Based on the conversion I have here and the known conversion of kilojoules to joules? You're all okay with that, huh? All right. Now the reverse problem here, what if we have 5.031 megajoules and we're trying to get to grams? Well, we've got this in kilojoules, so we may as well just do the same thing here. And we'll do 1 megajoule down the bottom, 1,000 kilojoules on top. And again, we've got this relationship here. We've got D, and D is 2 moles of D. And then we've got minus 1752 kilojoules. So you see the kilojoules will cancel here. So that's moles. We need to get that to grams, and we do have the molecular weight, 5.3 grams of D over 1 mole of D. And that'll give the result for that one. Does anybody have any questions? Anybody have any questions about either of 15 or 16?
So how did we get 2 mole D?
2 mole D? Well, it says it's after grams of D, Michael. And see how it's got the 2 in front of the D here?
Yeah.
Yeah.
So 15 will be 1 mole A because it has 1 before it. For 15? Yeah.
15? No, it's 2 moles of A because it's got a 2 in front of the A.
Oh, okay.
And that's where I got that from up here.
Thank you.
All right. Any other questions? All right. How are you all feeling about 15 and 16? 10, 9, 8, 7, 6, 5, 4. You're all okay. So you're all feeling pretty good about those. It's good. All right. Heat and work. This last one. Okay. This is one that I never had a chance to go over with you, at least not in class, but I will go over it now. But sort of more on a superficial basis because, you know, it's actually not that hard. I'm not going to give all the background to it, but what happens is if you've got Q, which is heat, and then we've got W, which is work. And the clue here is to look at what absorbs and releases means. So absorbs means Q is positive. Releases means Q is negative. So when something absorbs heat, it goes up, which makes sense. When something releases heat, it goes down. That also makes sense, I think. It has less heat than it used to have. That's why it's negative. For work, when work is done on the system, that means W is positive. So it's like we're adding work to it. When work is done by the system, it's almost like it's releasing work, you can say. Then the W is negative. Does anybody have any questions? If you want a greater explanation of this, I'd suggest you go back and watch the Zoom session that I uploaded for this. It'd be the first one after spring break. So the delta E is going to be Q plus W, but the sign is going to be dependent on what the words say. Now in this case, absorbing 63, so it's positive 0.63.21 joules. And work is done on the system, well, it's going to be positive as well. So it'd be plus positive 12.08 would be the answer. Then we just add it together. And that would be 75.29 joules. All right. Now, if it said work done by the system, then it would have been a negative value of 12.08. If it was releasing 63.21 joules, then that would be a negative value. And just do it accordingly. It's not very difficult, really. Does anybody have any questions about number 17? Okay, how do you all feel about number 17? Be honest. You might not feel good about it at all because you might not have looked at it. That's okay. Okay, 5 more seconds. 3, 2, 1. Okay. All right, does anybody have any questions? All right, for those people who understand halfway, it's most likely because you haven't looked at it yet, and that's fine. But go back to that first Zoom session and see the explanation I put forth there, and I think you'll have a much better understanding of what's going on. All right, does anybody have any questions? Any other questions about test 3? All right, so what I would suggest you do is on the test, when you take the test, I only go down and look at the work if it's wrong. And even then, you have to email me to tell me to look at the work. Right? That's how it goes. So if you got an answer wrong, but you've done the work for it and it's in the box, then email me, tell me the work's in the box and you would like some partial credit, and I will go and do that. So if the answer is right, then you don't have to worry about it so much. But if the answer is wrong and you haven't put the work in, then you're not going to get any credit at all, any partial credit. So that's how it's going to work. Does anybody have any questions?
So were we supposed to show our work for every question?
It's up to you, Alex. I mean, it's what you feel comfortable with. If you're very confident in your answer, you don't have to show the work, right? Because the answer will be correct and it'll all go through. But if it's a gamble, isn't it?
Yeah.
Yeah. Are you willing to take the gamble, Alex? How lucky do you feel?
I think I'm pretty
Yeah.
lucky.
Yeah. All right. Well, I'm just saying that those are the conditions. If you want the partial credit, you're going to have to do some work for it. That's my
All right. Thank you.
That's my thought. All right. Any other questions? So all the quizzes, those are due on Sunday 11:59 p.m. The credit quizzes. Is anybody uncertain about how to access the credit quizzes? By now you should be okay with it, I think. My recommendation, and this is what I would do if it was me, just me. Let me get out of here. If it was me wondering, oh gosh, I don't know which quizzes I've done, which quizzes I haven't done, what am I going to do? I have no clue what's going on here. How do I know? All right, so I'm going to view as a student here. Okay, so you go to grades. I've given you this suggestion before, but I'm going to do it again anyway. Look at test 3 and look at the scores on these credit quizzes and see what you have got a 0 on. And most likely you haven't done that quiz. And all of these quizzes are in the different folders in the test 3 folder. All right, so you have to do the practice quiz, get 80% on that. Then you get the credit quiz, you get 2 attempts at the credit quiz. It takes the highest one. You don't have to get 100% to get the credit. You get whatever you get. These are all extra credit, every last one of these. Now the number of points, the way the points add up, you add up all the points, you divide that by 2. That tells you how many points you're going to get added, and these get added to your test score. All right, does anybody have any questions? Anybody have any questions? Any questions?
I have a question about the lab, but I'll do that after class.
Okay, Code. All right, any other questions? Okay. Well, and I recommend doing the test early. That would be my thought. Do it early, get it out the way. Don't leave it till the last day to do it. And I think you'll be a whole lot more successful. All right. Well, then I'll leave it here for today. Good luck. If you need me, email me. I'll talk to you later.
Thank you, Professor.
Nice weekend, Professor.
Have a good day.
You too.
Coden, hang around.
Will do.
All right, looks like it's just you and me, Coden.
All right, so I got back the feedback for the lab book, and it said I think it's extinction coefficient.
Yeah.
What is that?
The slope.
Okay,
slope of the graph.
Best fit, right?
Yeah, the slope of the line of best fit. Okay. My recommendation would be for you to do it by Excel, but for some reason I don't understand why it looks like the concentrations might be wrong or something. I don't know, but you're getting the concentration values are way too high that you're picking up.
Okay, see, that was my other question. Do I use the equation 1 where it's A equals EBC
to get the concentration?
Yeah.
Well, once you got the slope, yes.
So, but before that though, then no.
Before that though, okay. Well, let's go back and take a squiz at the lab. Okay.
Because I think that's what threw me off then.
Yeah, let's take a look. I need to figure out exactly which part of the lab you're talking about.
All right.
So we'll get to that. Let's see. So this is a video on how to plot a graph
Right.
in Excel to find line of best fit. I recommend you do that. That'll give you a much more accurate. That'll give you a much more accurate number for that. Excuse me, for that slope.
I figured I might as well try it handwritten, and then if it didn't work, then I'll go to Excel.
Yeah, well, it didn't work. So.
No.
But that's okay.
Yeah.
All right, let's have a look at lab manual. I just want to.
There's a final for this class, correct?
There is a final for the lab final. Yeah, for the lab there is. Yeah.
Mm-hmm. Okay.
Yeah, take a look at the syllabus.
Yeah.
Yeah, let's have a look. Nice one to be.
Page 90, I think.
Yeah.
Well, that's the calculations page, at least.
Yeah, here we go. All right. Hang on. Next one. There we go. All right. Okay, let's have a look. Yeah, I think what it is that you haven't used the correct initial concentrations of those solutions in order to make the graph in the first place.
Mm-hmm. So I use? Oh, sorry.
It's important that you make sure you get the right dilution, right?
Right. I think I'm just using the wrong formula.
Okay.
I tried to use the equation 3, which is C1 equals C2 times V2 over V1.
Yeah, that's right.
Maybe I can't really see it. Hold on.
Yeah, that's what you should be using.
But I couldn't find V2.
Well,
would it be 100 milliliters?
Well, no. If you look at the procedure, can you see it here? It says obtain 50 mils of stock solution, right?
Yeah. So is that what I use? 50 mils?
Yeah, I think so. Because then
I was just wondering because I didn't see it on the student lab, and normally we only use the student lab info. So I was just looking
right, but sometimes hang on. Let's see. So let's see. Label 4. I just want to look at that. I'm just going to verify this. No, actually, I might be wrong about that. Hold up for a second.
All right.
Okay. I just want to see what size the volumetric. Okay, there's the volumetric flask. Okay. All right. So this is the story. V1. C1 would be the initial concentration of the stock solution. Okay, which I don't know is given. Should be given to you in the lab data, right?
Would it also be molarity?
Yeah, that's the molarity of the stock solution.
Okay, so then I think that's 4.77 to the -5th.
All right. So that's times 1, right? That's the volume divided by 250.
Oh, okay.
Because that's the volumetric flask. That's what it's been diluted into.
Okay. So when it asks for molarity of 1 milliliter standard solution or 1, 5, 10, 15, you would do 4.77 times 10 to the -5th times 1 divided by 250?
Yeah.
Okay.
Divided by whatever multiplied by whatever volume you have.
Whatever it's asking for, right?
Yeah.
Okay. So
yeah, because what you're doing is you're taking the initial solution, you're diluting it into 250 mils, which always sends it down, sends the concentration down.
Yeah. Okay, that makes way more sense, and that would explain why my
Now, but if you look at the absorbance, the 1 mils of a standard, these are all standard solutions. Those are all given to you, right?
And you just plug those in. You multiply that times the molarity of the stock. Right.
Hang on. Volume, calculated data. Yeah, the molarity. You see the molarities. Yes, these molarities here. You're going to get that from the stock, just like we talked about.
Okay. And then each time divided by 250 milliliters.
Yeah.
All right, got that.
And then you should be able to get in the line of best fit.
Yeah, because I was wondering why my line of best fit was the same as the molarity of the stock.
Yeah, it just doesn't work out. Yeah. All right.
Yep. All right.
Okay.
That helps everything. Thank you.
Okay. Bye, Code. I'll talk to you later.
Day.